Hello and welcome to my talk about optimizing packet scheduling and path selection for anonymous voice calls. I'm David Schatz and the co-authors of the paper are Rossberg and Guenter Schaefer. Without further ado, let's jump into our motivation. The context is onion routing, for example, as implemented by the Tor network. To recap, onion routing enables anonymous communications by relaying uniform-sized packets via multiple hops, which I also call mixes throughout my talk. In addition, packets are encrypted in layers to transform the bit pattern at every mix. By setting up so-called circuits beforehand, this may use symmetric ciphers. In result, onion routing seems to be a promising approach to implement anonymous voice calls, for example for a counseling helpline. However, there are challenges. First, interactive voice calls have strict latency requirements. The mouth-to-ear latency should not exceed 400 milliseconds to provide acceptable call quality. Hence, path selection for circuits should consider latency between mixes. At the same time, capacity of mixes has to be considered. Otherwise, congested mixes increase latency or packet loss. Another challenge is to defeat network flow watermarking attacks. That is, if attackers manage to drop or delay packets at a sender Alice, this pattern should not be recognizable at her communication partner Bob. Last but not least, some users may actually not only require relationship anonymity, which means to hide their communication partners from third parties, but also location anonymity, which means to hide their IP address from their contacts. To the best of our knowledge, there is no approach that tackles all three challenges. And while there are individual approaches for each challenge, it is not obvious how to achieve everything at the same time. Now, our contribution is to formalize a model in which all challenges are addressed and use it to answer the following research question. What is the best latency we can hope for, given all the other constraints? To tackle this question today, we start by formalizing two packet scheduling strategies that defeat watermarking attacks. Then we derive a mixed integer linear program whose solution can be mapped to a probabilistic path selection. The linear program minimizes latency of circuits, but also takes capacity into account. Next, I present our results for solving the linear program on a latency and bandwidth dataset that we obtained from the real Tor network. Last but not least, I conclude our findings and give some ideas for future work. But first, we make some assumptions. The first is the existence of a directory service similar to Tor. Its task is to collect all information about available mixes. As motivated, this includes both the capacity of mixes and their pairwise latencies, both modeled by a weighted graph G. Given G as input, we further assume the directory service to determine probabilities for path selection and distribute them to the users. Next, we assume that dialing and circuit setup may be realized without leaking additional metadata, compared to the metadata leaked while the calls are active. We further assume that all users use the same path length for their circuits and denote the different positions on a circuit as layers. To achieve location anonymity, we assume a rendezvous mechanism similar to Tor. That is, users agree on a rendezvous cookie during dialing and use it to instruct their circuit endpoints to connect the two circuits. Next, we look at two packet scheduling strategies. The first is inspired by batch processing as in classical mixed networks and was first proposed for voice calls in a system called Yodel. They suggest to synchronize the start time of many calls. Then, voice packets with the same sequence number are forwarded in lockstep from layer to layer. To illustrate this, when all packets are sent at the same time at the first layer, they will arrive at the second layer at different times. And only as soon as all packets arrive, they are forwarded at the same time again, but in shuffled order. The main problem with this approach is that if only one circuit uses a high latency link, latency on all circuits is equally degraded. Hence, and in contrast to Yodel, our goal is to avoid high latency links during path selection if that's possible. But first, let's have a look at an alternative approach to remove watermarks, inspired by the jitter buffers normally used at receiving voice clients. For this, mixes locally divide time into intervals which match the payload of voice packets in milliseconds, for example 20 milliseconds for many popular codecs. Then, when ignoring jitter, the ingress packet timing on a circuit may be modeled as a periodic signal. We denote the offset of this signal within the intervals as its ingress phase. Next, the sending times for the same flow are determined by a periodic signal as well. Consequently, even if the ingress packet flow does not perfectly match the periodic signal, the time between sending is guaranteed to match the correct interval length again. However, and in contrast to normal de-jitter buffers, the egress phase has to be random to mix packets of different circuits. And if the egress phase happens to be smaller than the ingress phase, sending times are moved to the next interval. In summary, this leads to a scheduling delay at every hop, namely half of the interval length on average. Our goal is to compensate this delay by preferring low latency links during path selection. We now derive a linear program for each scheduling strategy that minimizes circuit latencies. To understand the idea behind the linear programs, it is helpful to first assume that the total number of circuits and their optimal path are already known. Then, the situation may be modeled by a flow in a special flow network, not to be confused with packet flows for scheduling. In this flow network, users are collapsed to a single source node for the flow, and its target is the rendezvous layer. There further is one link for every possible pair of mixes on adjacent layers, and their flow values count the number of circuits that use the link. Then we can derive a probabilistic path selection that results in similar paths with high probability by normalizing the total flow value to 1. Finally, we can drop the assumption that we know the optimal path selection and instead use the flow values as variables in a linear program and solve it to get an optimal probabilistic path selection. So let's continue with an overview how our linear programs look like. First, there are constraints that express our flow network model, namely that the total flow at the source node shall be 1, and that all other nodes conserve the flow up to the rendezvous layer. Next, we introduce some constraints that shall guarantee a reasonable amount of anonymity. First, if a mix is used as entry mix, which can be expressed by a binary indicator variable, we force its probability to be selected to be at least a min. This is beneficial when attackers manage to identify the entry mix of a user, because on average, many others use the same entry mix. Second, there shall be a good mixing of circuits at all other layers. For this, note that when attackers try to attack the location anonymity of a user, they actually try to track its circuit in reverse direction. Consequently, we enforce a minimum in degree of d at every node in the flow network. When using batch processing, we further want to achieve a balanced path selection at every layer I. That means that the probability to select a mix at layer I shall be proportional to its capacity. Next, we bring latency into play. To express bottlenecks between adjacent layers, there are binary variables that indicate whether a link has a non-zero probability to be selected. Then, the maximum latency between adjacent layers may be expressed by the variables yi. Finally, the objective is to minimize the sum of these maximum latencies, which corresponds to the uniform latency on all circuits. When defining the linear program for the de-jitter buffer strategy, the capacity constraint looks slightly different. Instead of forcing a balance at every layer, it is sufficient that the total probability for selecting a mix at any layer is proportional to its capacity. And as motivated, the objective in this case is to minimize the average latency of circuits to compensate the additional scheduling delay. This is expressed by multiplying the link probabilities with the matching link latencies and building the sum over all links. Now we move on to our results for solving the linear programs. For this, we performed latency measurements in the real Tor network. In our paper, we further used the consensus weight of Tor relays as an estimation for their bandwidth. However, we used homogeneous mix capacities for the experiment I present today. Our raw dataset is also publicly available. Based on the raw dataset, we generated 32 random subsets for each parameter combination. Bar charts on the following slide will show the average across these 32 runs, and together with the 95% confidence intervals. To evaluate the trade-off between latency and anonymity, we look at two metrics. For one, we simulated calls using the resulting path selection probabilities and calculated their latency from entry mix to entry mix. To measure anonymity, we calculate the static probability of selecting a completely malicious circuit, which implies that a user does not have any location anonymity at all. We further fixed the number of mixes to 50, used a voice payload of 20 milliseconds per packet, and a minimum entry mix probability of 1 divided by 50. Additionally, we considered a strong threat model by assuming that the 20% of all mixes with the best average latency to all others are malicious. We first look at the results when using batch processing for varying circuit length and minimum node degrees. In the left figure, we can see that there is only one parameter combination that is able to consistently achieve latencies below 400 milliseconds, namely a circuit length of 3 and a minimum node degree of 4. However, the same combination results in rather bad anonymity. 1 out of 100 circuits will not provide any location anonymity at all. The main problem here, especially for shorter circuits, is that all mixes are used for rendezvous, and thus high latency rendezvous links cannot be avoided. In contrast, many parameter combinations yield an acceptable latency when using de-jitter buffers. Note that we plotted the 95% latency across all simulated calls here. The average is lower. However, the minimum node degree, D, should not be too low. Otherwise, greedily selecting the links with the lowest latency drastically increases the chance for a completely malicious circuit. For example, a circuit length of 4 and a minimum node degree of 16 yields a good trade-off here. In conclusion, we can say that in Tor, link latencies would be too heterogeneous to use batch processing for voice calls. In contrast, when implementing de-jitter buffers at every mix, good trade-offs between latency and anonymity are possible. Further note that de-jitter buffers are also more practical to implement. For batch processing, mixes actually require tightly synchronized clocks for sending all packets at the same time. As future work, we plan to develop heuristics for solving the linear programs. That is because, in its current form, solving it for more than 100 mixes takes too long to be practical. Furthermore, we want to combine the resulting path selection with Hydra, an anonymous messaging system we recently proposed. Hydra supports circuit setup and dialing with very large anonymity sets. Finally, I would like to thank you for your attention, and I would be more than happy to answer any questions. Furthermore, I listed the references used for the talk today.